already give a nice introduction to what you expect from FactProSim. Also very nice questions from the audience.
Yeah.
So I guess we can directly jump into the next slide.
Okay. Yes.
And Shivani, do you want to now introduce the FactProSim side of our nice pre-question table?
Right. So I will come back to this slide again at the end to tell more about it. But overall features is that you don't need any programming experience, and with FactProSim you can also model complex processes. And by the way, this tool is developed by Nishant Kumar, Professor Marie-Aline Van Ende, and Professor In-Ho Jung in Korea. And I think Marie-Aline is joining us today online. Is she joining? Okay, she's joining probably. And she also mentioned that being a developer, she would be very happy to take advanced level questions at the end. And today, what the example for the demonstration I have prepared is inspired from the BOF steelmaking process that comes with FactProSim and FactSage 8.4. Okay, so these are some of the features of FactProSim, and in this case, you can do iterative processes as well. Okay.
Okay, so maybe from my side, just to add on this, so we see two changes on the table from FactFlow to FactProSim. One is the powerful for advanced use becomes high, and support for iterative processes. So we say that with FactProSim, you can tame the complexity and focus more on the what matters to you. And we will introduce you more at these two example cases. One is more simple to show how to get work with it now, and then later we will look at a more complex problem.
Right. Okay. So do you want me to show the interface?
That would be really nice. Yeah, I guess we can start going.
Okay. So, okay, by the way, you can open FactProSim from the add-ons. Again, you can click on run, but I just have it open, so I will just open it from here. Okay, so this is the interface of FactProSim here. So you see on the top left, you can create a new process flow sheet, so which is what I have created. You can, okay, I want to hide this, sorry. Yeah, you can also save this. So probably I can also save this. I can save it with the name Mini. Okay. You can also load an existing flow sheet that I will show later. Here you can have different number of steps. For now, we will have one step, and there is a run button. And on the left side, you see 3 panes. So in the first pane, you already are aware of the input stream and the Equilib block, basically, from FactFlow example. In FactProSim, there is a stream module. So this you can use to mark the ending of the stream. You can also use it to recycle. So it is very versatile in this case. You can also split. You can also have heat exchanger, for example. Today, we have avoided this for our demonstration. You can arrange, for example, I can just drag the input stream like this. I can also arrange, so I can also arrange them vertically just to make it nicer. I can also arrange them horizontally, which is also when you're working with complex flow sheet, it should look uniform and handy.
We have a lot of modules there. That is a really handy tool to keep it neat.
Yeah. And what you also see is the scale bar on top. And when you have a very large flow sheet, it becomes like a map, and it focuses where you are in the overall flow sheet. Then we also have other tools. So very nice thing about FactProSim is that you can interact with your input Excel, so your parameters Excel from your plant or experiments. And also you can write to Excel, which also I will show you today. Before running the flow sheet, you of course want to check if everything is correct. And for that, we have this initializer. And also because you will write in Excel, there should be some unique process IDs. So to identify the equilibrium. So for example, here it's 1, so that it writes correspondingly. It can identify. Yes. So
now shall we make this
yes.
quick example?
Right. On the top, just before after this. So and on the top right corner, you see several units. So these are the units for the overall flow sheet. So whatever you define here, you can choose from here. But before making the flow sheet, I should load the CSV file. So I will load my CSV file, which I have prepared with the method I just showed. Okay, and here you see the location of my CSV file as well. And I can click OK. Yes. So, Ömer, what should we do now?
I guess we can now go into the input stream and name it, and
right.
We can maybe name it as a hot metal, and and the other one we can put oxygen, a very similar example case, so it's easier to compare with the previous case.
Yes. So I created hot metal, and I can connect this to this reactor.
So these are two different streams that will enter to the equilibrium reactor 1 in this case.
Right. And now if I go to hot metal
so
1,
double click to open, and
yeah. And here you see on the description, I can also write, this is hot metal stream coming from the blast furnace. I can also set local units here for this specific block. I can set local units. For now, I will just keep everything global. Here you have 3 ways to write your temperature, amounts, and pressure. So you can have it, you can just write it 1300, but what you can also do is you can link to the Excel. I will also add 100, and you can also write very complex equations. So if you are taking some gas mixtures or something, then you can basically write in the form of equation to define an input stream. Components you can add. So first thing, let's say I want to add iron. Just when I write iron, everything that contains iron pops up automatically in this program. I can, okay. And then everything that contains iron, I can write, and let's say I want to write carbon, but I don't want to calculate. I can write balance, and you can click OK, and it can normalize it to 100%. So it can automatically calculate when you have multiple species. But I have prepared an Excel for this, so I will show you how the input Excel looks like. Right. So we have these amounts. So this amount of metal and 100% oxygen that will be added in the process. So I will go, wait. So I will go to Excel link. So I will click on yes, I want to connect to Excel. Then it will ask me the location of the Excel, which I have directed to where I want to select from. And on the top, you see the name and the location. And also you can navigate between different sheets in FactProSim. And one very nice thing is I can just drag my mouse over these cells, and I click on OK. And I click yes, so automatically that gets filled in, and everything, all the phases that contain these species directly appear. So yeah, so in this case, I have the iron liquid phase, so I will select iron liquid phase, okay. What I can also do here is that I can select oxygen for my process. Oxygen comes in at 25.
Yeah, to be similar to previous example.
Okay, right. And this I can write pure oxygen. So you can write some equations if you are using different atmospheres.
So this description does not actually affect your calculation, but just to have to keep the information stored in each equilibrium object.
If you're taking some composition from a specific run in your process, you can write all those details in your description. Okay. And then I have the equilibrium reactor. I can also set this up. So I can set this up to 1600 degrees, right? And this is the reaction between hot metal and oxygen. Here you can do, maybe before this, I should have added the stream. Yeah. So I will split it into gas phase and then the condensed phase, as I did with the previous example. And then you see that on the left, you see the incoming streams and then the outgoing streams. I can set the temperature to 1600. In this case, I can also do adiabatic processes. So you can set the enthalpy to 0 and you can find the corresponding temperature. So, yeah. Okay. So for now, I select everything. Yeah. Yes, then I want to set the output stream. So in the case of gas, I want to select only the gas phase streams that come here. And what is also nice here that not only you can set the local units, you can also set the units for printing your Excel file. So you don't have to recalculate at the end. For now, I have selected the global units. And here I have selected only the gas phase that pass through, only gets collected into the stream. In the case of the condensed phases, you see it is very intelligent. It understood that the gas phase will go to the other phase. So I cannot select the gas phase here. But what is remaining is the solution and the pure solids that will go into the condensed phase. So this is also very much possible.
So now do we run the script or we go to the bigger example case and maybe show the examples from that on? Maybe we can do that.
Okay.
Yeah.
Okay.
So
okay.
To also be on time,
Okay.
maybe we can move again back to presentation.
Okay.
So we again remember this application case for our steelmaking, and this time we have this example to focus rather on one single process, but we will add more details which we did not cover in the previous process, such as these 4 cases that are described, the thermodynamics, the kinetics. Now we will add some kinetic constraints using effective equilibrium reaction zone. And we can consider more complexly mass transport and heat transport in the process. So coming to LD converter, maybe we can move to next. Are you familiar with the basic oxygen furnace process? Maybe you can hands up. I guess most of you come from a steel background. What I didn't know actually that the basic oxygen furnace, the name comes from comes from the base we put, such as the dolomite, the calcium oxides. It's not fundamental. That's something I learned while studying this. So it is a complex process. It is done to obtain steel from the iron we got from our blast furnace. It is the second part of the second part of the primary steel making that we used to produce 1.8 billion tons last year. So this is an important technology. And in next step, we try to model this with some simple assumptions, because every model you can have cannot be a replica of reality. It's just an assumption. It just depends on your boundary conditions and the boundaries you set, how complex you can go. And this is a sweet spot we have, the approach of equilibrium reaction zone. You see, we have these different regions. We have the iron metal. Inside, we have the slag. We are blowing oxygen to have these bubbles and to get the carbon out, and also the other impurities. So today we will show you this, how we modeled in using FactProSim. Yeah, what is effective equilibrium reaction zone? We define for this process 3 different reactions. The first one is the reaction between the hot metal, the liquid slag, and the oxygen that we blow. So this is this region happening. And the reaction B is the homogenization and melting of the scrap in hot metal. So we have 2 components here, metal and scrap. And we have also a reaction going on we define as reaction C, homogenization of slag and calcium oxide, a dissolution in slag. So the flux, the base here.
Yeah.
If you look more detailed, we have the data that we want to model a bit more detailed in the flux phase. We want to put 0.25 tons per minute. So we now can put the time into scale from first start to the first 10 minutes of the process, which is a 15-minute process. We will be putting this flux, and then we will change this ratio so we can actually at the effect of kinetics and your constraints regarding your process. And we do this, and the gas, we provide this in room temperature, and then slag and metal is provided in higher temperatures with 2 tons of slag as beginning, and then 100 tons of metal. And of course, the metal is not only iron, but it contains impurities, and the slag has also, containing some oxides, calcium oxide, iron oxide, and silicon dioxide. And this is, if we think about the flow sheet approach for our process model, this is the reaction A. They react each other. We can think about each separately, reaction B and reaction C. Here today, for the simplicity, we do not add scrap. And then, of course, this is actually more complex. There is a flow in the process, and we have some constraints. These are here shown as the A, B, and C. We call these kinetic factors in this equilibrium reaction zone approach. And you can see for the reacting metal, we can define different kinetic constraints at different time of our process. Here, first minute to 5 minute, we have 10% of reacting metal as a kinetic factor. Then we can increase this factor. We can play with this also for other steps of the reaction. And I guess now is the good time to move to FactProSim back.
Right. Okay. So this was the example that we created, but I can load the full example. And before closing, it's asking if I really want to clear it. Otherwise, this will be lost. So it's a good reminder to save the flow sheet. So I will say, okay, I don't want to save because this was just an example. Okay, so this is the overall flow sheet for the processes that happen inside converter. I will go into details of this, but firstly, you see that there are different colors for different streams. So the input stream is yellow color. So wherever you see input, it's yellow. And the green is the output stream. And the reactor blocks are in orange. So yeah, so basically we start from the hot metal, gas, and liquid slag, and with the effective equilibrium reaction zone approach, only part of the hot metal will react, and some part will not be reacting. So, and only the reacting part will contribute towards the equilibrium calculation. This will also happen in the case of gas and also the slag. So the reacting hot metal, the reacting oxygen, and the reacting liquid slag will then further react together to form reaction A, which is the reaction between hot metal, liquid slag, and oxygen. After that, we will have the reacted hot metal, and the gas will escape the system, and also the reacted slag. The reacted hot metal will then further react with the non-reacting hot metal from before, And at this point, if you're adding scrap, which we have avoided in today's example, so this is the place where you can also add scrap. And this will then contribute to reaction B, which is the homogenization in the hot metal. And essentially, then we produce hot metal final, which is the final steel that we form. And because they all will stay in the converter, therefore, in this case, we can recycle them to further participate in the next time steps reaction.
So maybe now we can look into hot metal and see what is
Right.
inside.
Yes. Okay. Yes. So I double click on the hot metal, and this is the parameters that I have set. So I have set the temperature from the Excel. So I can click on this I button, and you see that I have 1300 degrees temperature, and I can click on OK. Yeah. I have also set the amounts and the compositions that I have showed, and also the right phase at this conditions, which is the iron liquid phase. Yeah.
So again, all the species, as soon as we select, we see them, the related species from our CSV file inside this menu, so we can select or deselect each phase.
Yes. Okay. And what is very important in this case is that this total stream will be going to us. In real life, it will effectively react with the effective equilibrium reaction zone approach. And this is a kinetic in nature. And to incorporate the kinetic processes, this can be done in FactProSim using a splitter. So here I have added a splitter. And basically, I see the incoming stream, and there are two outgoing streams, which is the reacting hot metal and the non-reacting hot metal. I can set the kinetic constraints here using Excel. So you see here, metal A% will react, and then the 100 minus A will not react. So I am setting the 10% kinetic factor reaction for the first 5 minutes. And from the 6th minute to 15 minutes, it will increase to 30%.
Shivani, may I ask, like, how does the software understand that it needs to read whole columns?
Yes. So basically, this is a 15-minute process. So I have set the steps to 15. But if you want to simulate 30-minute process, you change the step number there, and then it will read different lines.
If my Excel file has 13 steps,
Yes,
then it
yes.
will read that.
Yes. Okay. And then I click on OK. For the mass balance purposes, one of the stream has to be balanced. So that it is satisfied, and you can check this again in the schedule button. So in the schedule, you see the overall summary of this unit block that you have selected. So you here can again verify that from 1st to 5 minutes, I have 10, and it will calculate the remaining in the non-reacting hot metal. And from the 6th minute to 15 minute, again, it will calculate so to be 70. Okay, so this is what I can do. And then I have also set some reactions. So basically reaction A with the corresponding phases that I want to form. And yeah, in this case, because I want to have adiabatic processes, so I have selected the enthalpy to be 0 from here, from my Excel file that I have. And you can also see in the schedule that I have a pressure of 1, enthalpy of 0, and temperature left empty, meaning that temperature will be calculated in this process. Okay. Yeah, and similarly, I have set the other reactors. I wanted to show about flux because we are changing the amount of flux that we are adding for different steps. And this also, I have selected first the right phase, and I can see that I'm adding flux. So this is the time, temperature, and for the first 10 minutes, I am adding flux, and after 10 minutes, I stop adding flux. Yeah. Okay. So
maybe it's a good time to run and then
yes. Okay.
show the results.
Yes. So before running, I have to click on the initializer, and you see it says everything is initialized. So I think we're good to go. And now I will run the flow sheet. For running, it will ask where you want to save. So I will replace it over my previously calculated. And you see it is running, and thankfully it does not take 15 minutes to simulate a 15 minutes process. It just takes, right.
That's why we use these tools, right?
Yes, so it took me 13 seconds and 657 milliseconds to run a 15 minutes process, so which is very fast. Okay, and let's look at the results. Okay, so for results, one thing to note is that for every green blocks and every yellow block, we have one Excel sheet of their calculated results. And the results are very smartly organized into the user, thinking into the user's perspective of what is more important. So when I go to the results, first, most important thing for me is to see how the reactions occur and what are the thermodynamic properties that I get out of them. And so this corresponds, so the reaction 4 is actually the block 4, which is reaction A. So 4, 5, 6 are basically reaction A, B, C. So this is the reaction A. And look at the delta H in joule is minus 0.0002 joule, which is basically 0. So we can calculate the adiabatic conditions, and correspondingly, we obtain different temperatures for the reaction A to occur adiabatically in the process.
Shivani, maybe is there a more fun way to look into our results?
Yes. Okay. Okay, so you can have different ways, but more fun way would be to create another Excel which can link to this Excel. And you can see I actually created a temperature profile for adiabatic conditions. For this overall process, and see how the temperature of the hot metal and slag evolve as a function of time. You see at 5 minutes, I see a change in the slope for both of them, and this is because of changing the kinetic factors. And at step 10, the temperature is changed because I'm no longer adding flux. So you can actually see the changes that can occur. What you can also get insights about is that the composition of the final steel that I'm making. So this is my steel in the beginning, the composition of the steel, and this is the composition of the steel at the ending. And you see that I purify the steel, and I'm also lowering the impurities in this case. You can also see which phases you are forming and how much. So this also gives a very good insight about your overall process, and remember, as a function of time. And the last thing I wanted to say today is not only you get the phases formed, but also you can get within a phase, the phase compositions that are present. So these kind of insights you can all get from FactProSim. So to summarize.
Also, one more thing, maybe.
Yes.
So the one advantage is that you once set up such Excel sheet,
Yeah.
and then you, for example, change something in your process
Yeah.
flow sheet, and you recalculate it.
Yes.
Then you can just directly visualize your results.
Yeah.
With the same setup, so you don't need
Yes.
to do it
Yes.
again and again.
Yes, so here you can link this to the other Excel, which I have linked to the output Excel, and automatically your graphs get updated, so you don't have to plot every time. Yeah. Also, what is nice is that in the input, if you want to, let's say, not calculate at 1300, but calculate at 1600, then when you change it, because the FactProSim will read that specific cell value, so it can recalculate the whole flow sheet when you make changes to your input Excel. Yeah. So
Thank you, Shivani.
anything
And
else?
I guess that's all for the sheet. And now we can go back to our table.
Yes. So it can account for advanced cases compared to FactFlow thing, like adiabatic conditions and integration of Excel and many more features like the time and the scheduler you can see. And it can also account for the iterative processes.
Thank you very much.